If you've ever bought shrimp at the grocery store, you may notice that there's different sizes of shrimp, right? But they're marked in kind of a weird way. They sell shrimp by count, which is the number of shrimp per pound. So if you pick up a bag that says 21 to 50 count shrimp, that means in a pound, you'll have 41 to 50 individual shrimps in there. They're not all exactly the same size, so they're not going to tell you exactly how many are in there, because then you get mad when it wasn't exactly right, and then give you this range. If there's a smaller count, that means you've got larger shrimp. So tiger prawns are those really big jumbo shrimp, and those might be only 10 to 15 in a pound of shrimp. When you buy a pound of shrimp, it's a pound of shrimp, but the difference is how many individual creatures do you have in there, right? So we can count shrimp by weighing them. If you have a 2-pound bag of 41 to 50 count shrimp, each pound has 41 to 50, so 2 pounds would be twice that, 82 to 100 shrimp. Any questions? Why the heck are you talking about shrimp? Well, we have a similar concept for atoms. That's why. We often need to know the number of atoms in a sample. The mass of a sample generally is pretty easy to determine, but the number of atoms in there, you can't count them, right? Why do we care about the number? Because chemical reactions happen between individual particles. If you have a reaction that's making water molecules, you have 2 hydrogen atoms and 1 oxygen atom combined to form 1 molecule. And that process is exact. It's always 2 to 1. Okay? So we are interested in that aspect, and so we often want to know how many atoms are in the sample. When we want to know, so we count them by weighing them. Regular sized objects that you can actually count, we have units for, like a dozen. How much is a dozen? 12. 12 what? Items, things, right? Could be anything. Could be a dozen cars. Could be a dozen pickles, dozen donuts, dozen pancakes. Doesn't matter. Dozen means 12 of the thing, right? Do you know what a gross is? No, it's not gross. A gross is 144 objects. A gross is a dozen. 12 times 12 is 144. So like little glass vials that we use in the instruments, they'll come by the gross. And it's 144 of them in a box. Another counting unit we have in everyday life is ream. A ream of paper is how many sheets of paper? Anybody know? A lot. It's 500. Yeah. So a ream of paper is 500 sheets of paper. Okay? Well, those units are all too small for our purposes, so we have our own unit, sometimes referred to as the chemist dozen. Instead of 12 things, it's 6.02214 times 10 to the 23rd things. It's a really big number. This unit is called a mole. It has an abbreviation, MOL. But the mole is the amount of stuff that has 6.02214 times 10 to the 23rd particles in it. Could be ions, atoms, molecules, just things. That number has a name. It's called Avogadro's number because Avogadro's work led to the determination of what that number was. So, 1 mole of anything is 6.02214 times 10 to the 23rd units of that thing. This is a useful quantity of stuff. So this is a picture of a mole of copper atoms. 22 pennies would make up about a mole of copper. You can hold those in your hand, right? A tablespoon of water is approximately 1 mole of water molecules. So when we're dealing with 1 mole of something, it's not going to take up the whole room or require a dump truck to bring in, but it's also not going to be so small we can't see it or manage it. So it's a useful size. How did that number come about? The value of the mole is equal to the number of atoms in exactly 12 grams of pure carbon-12. We had another unit that talked about carbon-12. The atomic mass unit was defined as 1/12 the mass of a carbon-12 atom. So here we have the mole is the number of atoms in 12 grams of carbon-12. So 12 grams of carbon is equal to 1 mole of carbon, which is equal to Avogadro's number of atoms. We often just use 4 significant figures on Avogadro's number. This gives us the relationship between mass, the grams of carbon, and the number of atoms, and allows us to count atoms by weighing them. So we can convert between moles and numbers of atoms, and it's the same as converting between number of eggs and dozens of eggs. This is dimensional analysis. So if you're doing it with eggs, 1 dozen eggs is equal to 12 eggs. For atoms, you're going to use this conversion factor. 1 mole is 6.022 times 10 to the 23rd atoms. So we're still going to do that pattern where we put all the units in first, and then we stick the numbers in. And you've got moles of atoms on top and atoms on the bottom, and sometimes you're like, I don't remember which one the number goes with, right? Mole is like dozen, atoms are like eggs. So the mole is 1, and the atoms, the eggs, are the number. Because it would be silly to say that 1 egg is a dozen eggs. Is 12 dozen eggs, actually. 1 egg is 12 dozen eggs. Does that make sense? No, it's backwards. So it's always 1 mole and Avogadro's number of things. Let's do an example. Pure silver ring contains 2.80 times 10 to the 22 silver atoms. How many moles of silver does it contain? So this is a thinly disguised dimensional analysis problem. So we want to look at what information are they giving us, what units are they giving us. Well, there's only 1 number in the problem, so that's probably important. It's this many silver atoms. And what are they asking us to find? Moles. So we're starting with 2.80 times 10 to the 22 atoms, and we're trying to find moles. Atoms are like eggs, moles are like a dozen. We know the relationship, so we can do that in a single step. 2.80 times 10 to the 22 atoms, 1 arrow, 1 conversion factor, mole goes on top, because Dora's going along and saying atoms to moles. Oh wait, it's an easy day for Dora, just 1 thing. Atoms to moles, and then we take this unit and bring it down because we need the units to cancel out. So we don't need to remember I'm supposed to multiply by Avogadro's number or divide by Avogadro's number. We do dimensional analysis, we put in the units, and the units tell us what to do. Less thinking, more correct answers. So we need numbers in here, and we know that there's a 1 and there's Avogadro's number. Where does Avogadro's number go? On the bottom with atoms, because those are like the eggs. A dozen is 12 eggs. A mole is the funny number. 6.022 times 10 to the 23rd atoms is 1 mole, just like 1 dozen is 12 eggs. So be sure to get your calculator out. Avogadro's number is one of the reasons that we have to know how to use scientific notation on our calculators, because you can't type that number in decimal form. I've never met a calculator that can do that. So 2.80, and then times 10 to the is your EE button, or your EXP button. And then I enter the exponent, 22, times 1 divided by 6.022 EE 23 equals. So this is giving me a whole bunch of digits. I don't like writing down a whole bunch of extra numbers, so I'm going to ask myself, how many sig figs should the answer have? 3. Because our starting number had 3, and we rounded Avogadro's number to 4, so this is the one that limits. So I need 3. I'm going to write the 3 down, and I'm going to copy down the next 2 just to be safe, and then I'm going to round. Oops, not atoms, moles. Any questions? Does anyone need me to fix their calculator? Because if you do it wrong, you're going to end up with this same number, the 465, but you're going to have like times 10 to the 45th power, something like that, which is not right. And that's just a miscommunication with your calculator.
Okay, that's what I thought, but I can still turn that into.
So we need one more thing to count atoms by weighing them. We need to know the mass of 1 mole of atoms. So we call that the molar mass. It's the mass of a mole. Atomic mass, mass of an atom. Molar mass, mass of a mole of atoms. Now this is really cool, and it wasn't an accident. An element's molar mass in grams per mole is the same number as its atomic mass in atomic mass units. And the reason it is that way is because they defined Avogadro's number so that that would happen. Okay? I don't think Avogadro actually knew what the number was. He was just the one that said there is a number. So if we look at aluminum on the periodic table, there's a number 26.98 underneath. Well, if we want the mass of an average aluminum atom, 26.98 atomic mass units. If we want the mass of a mole of them, same number, grams. Okay? So all of those numbers have 2 purposes. That's efficiency. So a mole of any element is the same number of atoms, but they're going to have different masses because an aluminum atom weighs more than a carbon atom. So if you have the same number of them, they're going to weigh more. So that molar mass is also a conversion factor, and it's one that we are going to use a lot. So 1 mole of carbon weighs 12.01 grams. Get that off the periodic table. That's the average mass. And so that can be a conversion factor with grams on the top or grams on the bottom. We don't really need to think about it because we're going to let the units tell us what to do. If you have not gotten a clear picture of dimensional analysis yet, today's the day to do it. Just keep asking me questions until that light bulb comes on. Calculate the amount of copper in moles in a 35.8 gram pure copper sheet. So this is dimensional analysis. What unit are we given? grams, 35.8 grams. And what do we want to find? Moles. We want moles. So just like we've done before, we're going to write down what we're given, 35.8 grams. And over on the right, we're going to write what we want to try to find. Well, we need a relationship between grams and moles, and that's known as the molar mass. And for elements, it's on the periodic table. So you look at the periodic table, and under carbon, 12.0, that one says 108.
Copper.
Thank you. I was just testing you to see if you're paying attention. Good job. Yeah, copper. Whew, that was a close one. 63.546. 63.546. And that is number 29. So its box on the periodic table looks something like that. Now, you may have questions about the number of significant figures in this molar mass versus one that you see on a different periodic table. In class, after today, I'm usually going to use just 4 sig figs in the masses because I have a bunch of them memorized that way. And really what we want to do is we want to make sure that the number of sig figs in our molar mass is not going to reduce the number of significant figures in our final answer. So 4 is generally safe for Chem 1A. Here, we're starting with only 3 sig figs. And so by using 4 or 5 over here, we're still going to end up with 3. It's all good. I'll give you a periodic table for the exam, and that will have 4 sig fig molar masses on it. You can use those molar masses. You can use the ones on the wall. If you get a slightly different answer, it will be different in the last significant figure, which means that it isn't different at all, because the last digit is always uncertain. So this tells us that 1 mole of copper weighs 63.546 grams. We know the relationship between grams and moles. We can do this in one step. 35.8 grams. 1 factor. It's grams to moles. And grams go down here. The grams cancel out. So here I've got 1 mole in the numbers with grams. So I'm going to have 1 mole and that number of grams. .8 divided by 63.546. How many sig figs? 3. So I'm going to write down a couple extras, and then I'm going to round it. Again, about the sig figs, you should always try to use the correct number of significant figures. Okay? And like when you turn in a worksheet or a lab, I can tell if you were trying or not. Because when you're not trying, you've got like 9 digits on everything, which is better than rounding too much, but it's a lot of extra work. Anyway, that's the answer. So here's the plan for counting atoms by weighing. We start with the mass of the element. We go to moles of the element. That uses the molar mass. And from moles of the element, we can go to number of atoms using Avogadro's number. So grams to moles to number of atoms. How many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure carbon. 1 carat is 0.20 grams. So what do they give us? And they give us the 1.3 carats. Oh, that's the wrong yellow. And what else do they tell us? Yeah, a carat is 0.2 grams, because we don't expect you to remember that. And what do we want to find? Number of atoms. Okay, so let's write down what we've got, what we're given. 1.3 carats, and 1 carat equals 0.20 grams. And then over on the right, we're trying to find atoms. Let's move that over a little bit. So when they give us more than one number, sometimes it's hard to pick which one you're starting with. Look at the units. This is a weird unit, but it's just a single unit. And this is giving us a relationship between two units. This is a conversion factor. So that's not the thing we're going to start with. We're going to start with the other one. We're going to start with this guy. So we want to get from carats to atoms. Well, is this going to help us at all? This will get us from carats to grams, right? Carats to grams. Okay, now things are looking a little better, right? The previous slide, grams to moles to atoms. Grams to moles to atoms. This relationship is the molar mass. This relationship is Avogadro's number. They're not given in the problem because we should know what Avogadro's number is, and this guy is on the periodic table. So we're ready to go. 1.3 carats, 3 arrows, 3 factors. Carats to grams, to moles, to atoms. Take this unit, bring it down in the bottom. Bring grams down so it cancels out. Bring moles down so it cancels out. And then I go looking for numbers. Well, they gave me this relationship. 1 carat is 0.2 grams. And this is where grams and carats are converting. So I keep the number with its unit. 0.20 grams is 1 carat. Where do I find the relationship between grams and moles? Molar mass on the periodic table, right? So the carbon says 12.010, it's 8, that one, yeah. Atoms to moles, Avogadro's number. Mole is like the dozen, so there's just one of those, and atoms are like eggs, so there's 12, except it's not 12, it's this weird number. And then it's up to our calculators. 1.3 times 0.2 divided by 12.0108 times 6.022 EE23 equals. So this is what my calculator is showing me. There's a cart of Surface Pro tablets over there, and somebody's just freaking out and beeping at us. Sometimes students just look at the beginning of this number and say, oh, 1.30. 1.30 atoms in a diamond? That's not going to work, right? There's this little thing that's easy to overlook at the end, E22 times 10 to the 22. Oh my goodness. It's worse than the mooing balances.
Yeah, but what?
The mooing balances. We haven't had an exam yet, so it hasn't been quiet enough in here. The balances do this self-calibration thing periodically, even when they're turned off. And it sounds like...
Okay.
Yeah.
Interesting.
It's utterly distracting.
That's so bad, it's good. So we end up with 1.3 times 10 to the 22 atoms. So you can never have less than an atom. You can't have a fraction of an atom. You can't say, I have 2.2 children. You have 2 children, or you have 3 children, right? So, yeah. Anyway.
Assume the other in the loop is now a percentage of
Doesn't count. How big is Avogadro's number? Really big. Avogadro's number of pennies would cover the Earth's entire surface to a depth of 300 meters.
Wow.
Right? Yeah. That's just a lot of pennies. That many grains of sand, much smaller than pennies, would cover the whole state of Texas to a depth of several feet. If you counted 24 hours a day for the rest of your life, didn't stop for anything, you would never get to Avogadro's number. So this is Avogadro's number in decimal form. It's really big. The national debt pales in comparison to Avogadro's number. So this is a critical thinking problem. A titanium cube contains 2.86 times 10 to the 23rd atoms. What's the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeter. And you're like, what the heck? So we've got this problem that seems kind of random. But this is the kind of a question you should expect on an exam. We have learned the pieces necessary to solve this problem, but we've never put them together like this. And since we're going to do it together now, this one won't be on the exam because it has to be a different problem. Right? So we read the problem. We're going to pull out the numbers, what we're given. We're going to write that down. So we're given a number of atoms and we're given a density. And what are we trying to find? Edge length. Well, that's not even a unit, but whatever, right? Okay, 2.86 times 10 to the 23rd atoms. And 4.50 grams. This is a fraction. Don't use the slash, though. That's only if you're typing. Per cubic centimeter. I've started grading worksheet 1, and some people did not take my advice to use density as a conversion factor, and they wrote the density like this, and then they ended up with the inverse of the answer because they didn't see how the units were behaving. So always write it like this, vertical fraction. And then we want the edge length. What might be a good unit for that? It doesn't tell us a specific one. Centimeters, right? Okay, well, what do we know about a cube? It's cubed. Yeah. The length of the cubed is its volume. So the volume equals L cubed. The length times the width times the height, they're all the same. So we're trying to find L. If we knew what the volume was, we could find L, right? What's a probable unit for volume here? Centimeters cubed. And I'm going to make this a different looking arrow. This is a problem where we have to use dimensional analysis and an equation. the dimensional analysis comes in, how do we get from atoms to volume? Yeah, we want to get to grams, so we're going to go to moles first. Moles to grams. There's a way to bypass that, but we're just going to be the tortoise and always win the race. So atoms to moles to grams, how do we get from grams to cubic centimeters? Density. The density. They gave us that relationship. So we're going to do a unit conversion, atoms to moles to grams to cubic centimeters, and then we're going to use this geometry equation. So 2.86 times 10 to the 23rd atoms. 1, 2, 3 arrows in our dimensional analysis problem. Atoms to moles to grams to cubic centimeters. Atoms down here. Moles down there. Grams down there. Now we need numbers. Some of the numbers are written here on the screen, some of them are not. 4.50 grams per cubic centimeter. Well, over here, I have grams and cubic centimeters in the same fraction. So 4.50 goes in the bottom because that's where the unit gram is. And if you really want a number up there, it would be 1. Moles and atoms. It's Avogadro's number, right? 6.022 times 10 to the 23rd atoms is equal to 1 mole. Grams to moles. Molar mass. Periodic table. Titanium. What's the symbol for titanium? Ti. Now the tricky thing about this one is even if you're looking for Ti, your eyes can play tricks on you because there's a TL, but Ti is up here. 47.867. Now I didn't really leave enough room there. 47.867 grams. Those were canceled. .86 EE23 divided by 6.022 EE23 times 47.867 divided by 4.5. How many significant figures should the answer have? 3. The number of atoms had 3 sig figs. Yes, that is a number of atoms. Is it actually a counting number? No, because one person could spend their entire life counting and not get to that many, right? Even if you could see them. And so that's not an exact number. Here's our density, also not exact, 3. So we want 3. I'm going to write down the first 3 digits. 5.05, underline that one, and the next 2 digits to avoid rounding errors. So we've got our volume. Here's our volume equation. I have L cubed on this side and I have volume on the other side. I want L on one side and the other thing on the other side. How do I undo cubed? Cube root. So I'm going to take the cube root of both sides. The cube root of the volume is equal to L. So L is equal to the cube root of 5.0518 cubic centimeters. And see how the units are participating here as well. I take the cube root of centimeters cubed, and I get centimeters, which is a length unit. So different calculators do Q roots differently. So I'll be happy to help you with yours during lab. We're still going to keep with the 3 sig figs. So 1.72 centimeters. You get a problem like this, I don't expect anyone to immediately know what to do with it. So if you get a problem, you're like, I don't know what to do. That's normal, okay? We're going to figure out what to do. Write down things that you know, and then sit and think about it for a little bit, okay? Any questions?